Hi guys, BuildZoid here, and today we're going to be taking a look at yet another RX 5700 XT PCB, but this one I'm actually kind of excited about because this one's got some really nice power stages. Now, it's not quite on the, like, there's other cards with nicer ones, but, well, there's one other card with nicer ones. But yeah, I'm pretty excited about this one. So this is the MSI RX 570, no, the RX 5700 XT Gaming X. That's what it's called. There we go. The pictures are from Tech Power Up, so big thank you to them for providing high-res PCB pictures in their GPU reviews, and I would strongly recommend you actually check their reviews out if you care about things like temperatures, heatsink performance, power consumption, you know, the things I don't cover in my PCB breakdowns because these are meant to be about the PCB, not about the actual performance of the card. So yeah, there will be a link to their review of this card down in the description below. So with that out of the way, let's get into it. Now, this being an RX 5700 XT, it's got a lot of different VRMs. So we've got the V-Core VRM, and then under that, we've got what I suspect is the VSOC VRM. And I say suspect because I've still not confirmed for sure that this actually is VSOC. It could be VDDCI. It doesn't really matter, in my opinion, because VDDCI and VSOC on, like, pretty much every card ever use the exact same components. So it's really just like, I might have the names switched around, but it doesn't really matter which one's which because they're physically the same thing. Right? They just provide power different parts of the chip. Anyway, this over here I suspect is 5 volts because the power stages here actually need a 5 volt rail to run, and you only get 3.3 volts and 12 volts from your PCIe slot. So you need to get your own voltage regulator for that. Then over here we're going to have the, I'm actually not sure if MSI has the rest of it. Yeah, they do have it on the back. So these down here on the card are going to be, there's basically 2 more voltages that you need. So you need 1.8 volts, which is for like the BIOS chips, as well as all of the GDDR6 chips. That's a supporting voltage for them. And then there's also the PEX voltage, or wait, no, it's display drive PEX. Like there's another rail that's like 0.9 volts or something. There's another low voltage rail in this area for the GPU. I'm just not sure what it's officially called. Normally I call it display. I think it's display drive, and it might as well be, it might also include PCIe. Not sure right now. Anyway, so, you know, you've got your minor voltage regulators down there. Then this over here is what I suspect is VDDCI. So that's the memory controller power. And then we have up here the memory VRM itself. So that's VMEM. And that provides most of the power to all of the GDDR6 chip, because some of it also comes from the 1.8 volts. So that's all the different VRMs on this card. And let's start with taking a look at the most important one, the V-Core. So the V-Core here is an 8-phase, and it is controlled by this chip right over here, which that is an IR35217, which is the standard voltage controller for everything since Vega from AMD. For like, high-end, well, they've not put out any low-end cards, so we've not seen any other chips being used. But yeah, the 35217, like this is a high-end voltage controller from International Rectifier, goes all the way up to 8 phases total. Here it is running as a 4+1, and now somebody's going to be like, well, how do we have 8 phases? We'll get to that. So the +1 is for the SoC down here, so that's +1 phase from the 35217. The V-Core gets its 8 phases because on the back of the card we have 1, 2, 3, 4 doublers. So those are all IR3599s. They double, they quadruple. Here they're obviously just running in doubling mode, which is how we get from 4 phases to 8. They do not current balance themselves, but the actual controllers from International Rectifier are actually able to distinguish between the two like the controller actually can distinguish between this phase and this phase, even though they're both behind, like they're both on the same PWM signal line. So the controller can actually current balance through the doubler, even though the doubler itself is completely dumb and can't current balance. So that's kind of a neat feature of International Rectifier controllers, because there's a lot of other controllers out there which can't do that, and those need doublers that actually do current balancing for them. So yeah, anyway, so this is for, like, this is controlled like a true 8-phase. The only downside to using the doublers is they do add a little bit of delay to the PWM signals, which means your transient response is going to be, you know, not necessarily basically it makes it harder to get really good transient response out of the VRM, but transient response is also affected heavily by what kind of inductors you're using, what kind of capacitors you're using, how those capacitors are laid out, how the power plane is laid out, how many layers the PCB has. There's basically then the actual firmware of the controller itself will affect the transient response. So there's basically too many variables in the transient response performance to really go like, hey, if the card has doublers, the performance is going to be terrible, because it just like there's too many other things that could actually completely negate any impact the doublers had and get the card onto the same performance levels as other cards without doublers. Not that there's that many of those. Actually, there's quite a few of those for RX 5700 XTs. There's also quite a few cards with doublers, so that's worth keeping in mind. So I'm not really gonna, I don't consider it a massive offense to use doublers, basically. It's just like, well, they're there. They may or may not actually have a negative impact, but they definitely do make this VRM an 8-phase. It's just maybe not as fast as if you had an 8-phase that doesn't rely on the doublers. Though that's like the thing is, if your VRM can't respond so quickly, if you just make the output more stubborn to changes in voltage, then that's not really a problem, right? If it takes longer for the voltage to drop or rise, then it doesn't matter that the VRM is slower to respond, is slightly slower to respond, because really the delay the doublers introduce is like 5 to... what is it, like 5 nanoseconds for the shortest delay that they add, and then because the delay also depends on what exactly you're trying to, like what exact PWM pulse you're sending. And so actually once the entire VRM is active, you have like the delays are actually short. Because the one that's like the pulse that's most delayed is exiting tri-state. That's the transition that takes the longest for the doublers. And tri-state is only really like a concern if you're going from idle to full load. And normally by the time you get to like a loading screen on something, you're already running the VRM will already be running all of its phases at that point. Basically the GPU will tell the VRM to go to high performance mode long before you actually hit full power draw. So that's worth keeping in mind. Anyway, so yeah, that's the control scheme here. Now let's talk about the actual power stages. So this is where I'm really, really impressed with this card, because these are TDA 21232s from Infineon. These are 55 amp smart power stages, and they're insanely efficient. Like, absolutely ridiculous efficiency. They're very slightly worse than the 70 amp smart power stages that come in the 5x6mm package. These come in 5x5mm. Also, don't try to look them up. There's no public data sheet for them. But yeah, they're absolutely ridiculously efficient. Don't ask where I got my data sheet for. Well, I have my sources. Let's put it that way. That's how I know how efficient they are. Also, since they're a smart power stage, they integrate much more accurate current monitoring than what you'd get on some of the previous generations of power stages. Or, there's power stages that just don't integrate current monitoring at all. That's also an option. Integrated temperature monitoring and a bunch of integrated safety features like overcurrent protection and other things that I don't care about because they're details. So yeah, the end result is that this VRM is actually one of the most efficient RX 5700 XT VRMs you can get, even though it's not really like, it's only got 8 phases, right? These are only 55 amp power stages, but compared to a lot of the most cards are like 7 phases, and then 6 or 7 phases, and then there's a couple cards that are like 10 phase VRMs. Or in the case of Asus, you've got the Strix, which is a 10 power stage VRM, but 5 phases. Incidentally, that's the only VRM that's more efficient than this one. Because that uses like the full size 60 amp 5x6mm power stages instead of these ones. These are meant like they're all server grade parts, but these are like the more compact variant that is meant for high density applications. So these are not quite like, these can't handle the really high current outputs quite as well. Anyway, the end result is that this card is capable of doing, this VRM is capable of outputting 1.2 volts while running at a switching frequency of 600 kilohertz with 5 volts drive voltage, because that's just what these power stages run on. And it would be able to provide 150 amps while producing only 12 watts of heat, roughly. Unfortunately, the data sheet that is available for these is entirely spec'd in 1.8 volts, so I did have to try to convert that down into 1.2 volts through data sheets for other smart power stages, because unfortunately these don't have a voltage curve in there. It's just like they're meant for Intel servers, and Intel servers run on 1.8 volts. So that's kind of the one downside with trying to, like that's the annoying thing with the data sheet and there's a lot of parts like that. Like there's a lot of smart power stages where they're spec'd at 1.8 volts, and it's just like, but that only, like, if you're not building a Xeon based system, it's completely useless to have a specification in 1.8 volts, because it's just like nothing runs on that except Xeons and Intel CPUs with integrated voltage regulators. So mostly Xeons, right? And then I guess you can count the Skylake X and the Cascade Lake X CPUs as well, but those are just Xeons in disguise for consumers, so chopped up Xeons in disguise. Yeah, so I count those as Xeons. Anyway, 200 amps output. This VRM would be capable of delivering, 200 amps. This VRM will only produce about 17 watts of heat, which is nothing. Most other cards, you're looking at around 20 watts of heat output, which is already a great efficiency, but like 17 watts is a bit more efficiency. Then you go to 250 amps output, and this will produce about 24 watts of heat. And at this point, a lot of other cards are hitting around 30 watts. And then at 300 amps output, this card will produce about 34 watts of heat, whereas most other GPUs would be producing about 40. And 400 amps output, this VRM will produce about 56 watts of heat, whereas most other cards would produce like 70 or higher. Now, there's one card that actually beats these numbers, and that's the RX 5700 XT Strix from Asus. But that one's also insanely expensive, though it's not like the Gaming X is particularly cheap either, but this is still cheaper than the Strix. So yeah, it is really great to see a VRM that does such a, that's the thing. Smart power stages are pretty overpowered compared to what everybody, like most of the other RX 5700 XTs you look at are just using regular DR MOS components, which are also 55 amps, but they're just not built for the same level of efficiency that these are. So yeah, these are honestly, like, the efficiency of this VRM is honestly kind of ridiculous. It's really not far off of what you would get if you were running if this VRM was replaced with the 70 amp parts from Infineon, the efficiency would increase only a very small amount, which is also how I made sure that these numbers made sense, because again, the data sheet is spec'd in 1.8 volts, and I was like, luckily the 70 amp parts from Infineon do have a 1.2 volt spec. So yeah, these are some pretty impressive 55 amp smart power stages. I think they're actually probably on par with or not far off in terms of efficiency with the 60 amp ISL 99227Bs that are popular with high-end motherboards, or at least were popular, because right now Intersil also has 90 amp parts coming out, and those seem to be like ASRock's using them, MSI's using them. Anyway, we'll get to those when we get to those in motherboard PCB breakdown. So anyway, yeah, the VCore VRM on this thing is freaking awesome. When I first heard that this is just an 8-phase, I wasn't really that impressed. But then I saw, once I saw the data sheet for these, I was like, oh, okay. Yeah, sure, go, this is great. I love it. Now, the SoC VRM down here, this can push 25, this VRM down here can push 20, at the same operating parameters as up here. It could push 25 amps while producing only about 2 watts of heat. Then VDDCI is the same thing, because that's another TDA 21232, right? That's the thing, is just all of these are TDA 21232s. So everything on this card is basically a little bit more efficient than what you would get on most other 5700 XTs. So that's another TDA 21232. And of course, the memory VRM has 2 more TDA 21232s as well. So the memory VRM is capable of pushing a little, around 50 amps while producing a little over 4 watts of heat. So not exact, a little bit more than 4 watts. So yeah, the memory VRM here is also really, really efficient. Most of the other 5700 XTs will do 40 amps while producing about 4 watts of heat. So, it's not a huge advantage. It's just it's still an advantage though. And honestly, this is probably really overkill for the memory power delivery requirements of the 5700 XT. The controller for VMEM and VDDCI on this card is of course the NCP 81022, running in 2+1 phase mode. This thing has a public datasheet, which makes it incredibly easy to vault mod. Also, it's incredibly easy to vault mod because unlike say fully digital international rectifier controllers, this does actually have a straight up feedback pin. So if you use like a 10K trimmer, you can very easily adjust the output voltage. You can disable the overcurrent protection by basically desoldering one resistor, and goodbye overcurrent. Like, it doesn't have current limits anymore after that. So yeah, this is a very easy controller to mod. And actually, speaking of modding and voltage control, this right here from MSI, I'm a huge fan of, because you can get the Infineon voltage controller programming dongle, the USB 005, very, very easily. And then you just need to, solder a little 3-pin header onto the card, and you can plug that in, and bam, you get full control of the IR352217. Which basically means, you can tweak your SoC voltage, vCore voltage, you can tweak frequencies, you can tweak load lines, you can tweak everything. You can tweak the transient response configuration as well. So yeah, that like, I'm a big fan of cards which make it really easy to get to that set of connector, that, like, basically cards with this connector. I'm a big fan of that, because it makes, like, it's not impossible to get that connection directly off of the controller, even if it's not like highlighted like this, but this makes life a lot easier. So I'm a big fan of cards that come with the solder pads for that header, because it does make taking control of the controllers much easier. So yeah, anyway, other things around the card. So this card is one of the so one thing that's kind of disappointing with this card is that MSI doesn't have dual BIOS on it. So, great power delivery across the board, but there's no dual BIOS, which MSI does have a 5700, which uses exactly the same PCB as far as I know. So they have a 5700 Gaming X. And so, you might want to buy the RX 5700 Gaming X from MSI and then flash the 5700 XT Gaming X BIOS onto that, just to get a little bit more performance, bit more power limit, that kind of thing. And well, this doesn't have dual BIOS, so if you screw that up, you basically need to have a backup GPU. Which is a little bit less convenient than, like, there's a lot of other 5700s that will just give you dual BIOS, whereas this card, like, it physically doesn't have the, like, normally you'd have, like, on some cards you can at least, like, see where the BIOS switch would go, but here it's like there was never any plans to have dual BIOS on this card at all. So that's kind of the one thing I would complain about here, but at the same time, unless, like, BIOS flashing is not that dangerous and not that risky unless you're modifying the BIOS yourself. If you're just flashing, like, if you just take a 5700 XT BIOS and smash, like, put it onto a 5700, that's relatively safe, right? Unless you use a BIOS for a card that's like a completely different model and there's some kind of conflict between the like how your card is physically configured and the card that you've taken the BIOS off of is physically configured. It's relatively safe as long as you're not trying to, like, if you're flashing a Gaming X BIOS onto a Gaming X, it's fine. What would be concerning is maybe like a Strix BIOS onto a Gaming X. That might cause issues just because the VRM configuration is very different, though generally the BIOS shouldn't be configuring the voltage controller very much. Like, it can, but it shouldn't be doing that. So yeah, even something like that should be relatively safe. And the only real concerns are if there's, like, massive differences in terms of voltage controllers or memory chips. Sometimes you'll have a BIOS which doesn't support the memory on a certain card, and then you flash that and, well, you're screwed. So yeah, like, it would be nice to have the dual BIOS just as a, like, because it does make recovering from a bad BIOS flash much more convenient. But at the same time, it's just like, it's not really that risky. And you can also just do power play tables on 5700s if you just need the extra power limit and that kind of thing. So yeah, I would prefer if the dual BIOS was there, but at the same time, it's not like it's a huge deal in my opinion. And yeah, but I think, like, the thing is, it also doesn't really cost that much to add an extra BIOS chip and a switch. So I don't know, like, I guess depend. Like for me personally, not an issue because I have like I can recover the card even if like even without a BIOS switch. It just takes more. It's just more difficult to do. But if you don't have like spare GPUs, because basically you need to get into Windows somehow and then do the BIOS flash like fit to. I'm not going to get into that. Basically, you need a spare GPU if you don't have a BIOS switch. So that's kind of the sort of like one annoying thing about this card here. Now, another thing that MSI has added that like one thing this card isn't missing is fuses. MSI does have fuses on every single input. They're all 20 amps, which I honestly think is like 20 amp fuses up here, sure, whatever. Actually, you know, if it was up to me, I would be putting 30 amp fuses up here because 360 watts is not, well, like that's the normal power limit for one of these connectors. But hey, 20 amps, not really a big deal, right? That still gives you 240 watts for each 8 pin, so that's going to be like before you come to before you get into before you risk blowing the fuses while overclocking, you'd already have to be pulling over 400 watts into the card. So the fuses really only get in the way if you're on like liquid nitrogen or something and are really pushing it. You'd probably have to have manual control of the controller to you know run into that being an issue. Now the fuse down here is also a 20 amp, and I think this is just like you could use a 10 amp here instead because this is on the PCIe slot 12 volts. And it's just like, this is really like the whole point of the fuse here is not to protect the PCIe slot. It's to protect the card if, you know, some power stage blows up or something. But there'd be no harm in having a smaller fuse down here, in my opinion. And if you have a smaller fuse, it's far more likely to blow faster than if you have a 20. Right, like that's the other thing is you want the fuse to blow as soon as possible if there is an actual reason for the fuse to blow. So having an unnecessarily large fuse just means, well, you're making the fuse a little bit slower for no good reason. So that's the thing. I would have preferred to see a 10 amp down there instead of a 20, but still, like the fuses are here basically to protect, like the fuses here don't stop the card from failing. Like this, I think, is like basically if a fuse blows on a GPU, replacing the fuse does not fix the issue. Okay, the fuse blowing is a symptom, not the cause. The fuse is there to basically protect the card from further damage if something blows up. So let's say you have let's say one of the VCore VRM power stages blows up. You're basically going to have the issue that you're going to have a short circuit. It's very likely that you're going to have a short circuit to the output of the VRM. Now, these being smart power stages, that should be very, very unlikely that actually happens. But let's say it does happen. So you're going to have a short circuit from plus 12 volts to the output. The problem with this short circuit right here is that your GPU core, if it's exposed to like 2 to 3 volts for even a couple milliseconds, it's going to be very dead. Or microseconds. It really doesn't take long. Like, if you exceed the maximum voltage allowable for the silicon for a very short period of time, bye-bye silicon. So the whole point of these fuses is basically to blow up before the output voltage rises too high and to prevent power cycles. Because if you have a GPU where the power stage has blown up and then you power cycle it over and over and over again, every time you power cycle it, you're going to be having the output of the VRM go way high voltage for as long as basically for however long it is that it takes your power supply to trip the overcurrent protection, right? Or short circuit protection. So basically the fuse isn't here to prevent physical failure of the card, it's to prevent further damage after the physical failure has already occurred. So these help people who are like, fuses are good for people who are capable of repairing the cards. They're not actually like they're useful for people in the RMA center. They're useful for people buying dead cards on eBay. They're not really that useful if you have no idea what you're doing when it comes to repairing something. Also, don't send me questions about repairing things. I'm not a repair shop. So yeah, that's kind of the thing. But the fuses, like, they definitely make the card, they make it harder to actually destroy the silicon on the card. Because obviously, like, if the card fails, the most expensive thing on the card is the actual chip. So you want to protect the chip. That still doesn't change the fact that if the VRM blows up and like the fuse is blown, the card's not good, like, it's going to be a really hard repair anyway. Though also the fuse can limit things like how much, like let's say you have the short circuit in your power stage. If the fuse blows quickly enough, it can potentially prevent the short circuit from getting hot enough to do things like, melting through burning through several layers of the PCB, because that can sometimes happen where if you have a component fail and then you remove the dead component and you basically find the copper layers welded together under it because the short circuit just got so hot. So if the fuse blows fast enough, it can prevent the short circuit from getting hot enough to do that kind of damage as well, because obviously that makes repair far more difficult as well, because then you start having to like drill holes into the PCB to get the short circuit out, which on a multi-layer PCB is a very, very risky thing to try do. So yeah, that's kind of that for the 5700 XT Gaming X from MSI. Like it's a really nice card. I do actually I really like it. Oops. And yeah, so that's it for the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I do have a Patreon where you can support me directly. There's a link to that down in the description below. And if you don't want to use Patreon, I also have a Teespring store where there's shirts, stickers, posters, that kind of thing. So if you'd like to buy any sort of AHOC themed merch, there's a link to that down in the description below as well. And that helps out immensely with running the channel too. Like the Patreon obviously does as well. So yeah, anyway, that's it for the video. Thanks for watching and goodbye.